So hello everyone, it's Harsha from India. It's pleasure to be here at HPSF 2025 to represent my work under NSM, which is National Supercomputing Mission, which is initiated by Indian government to build a HPC ecosystem all over country. So we'll see what exactly NSM is. First of all, we'll see what exactly NSM is, because we are working on that systems, and the Kokkos is also deployed on the same system. So it's a visionary initiative to strengthen India's academic and R&D ecosystem through high-performance computing and deploying supercomputers across academic institutions, research organizations, and government bodies. So till now, we have deployed 30+ supercomputers across the country at the prestigious academic institutes and research centers of the government bodies. Our main focus on building a skilled HPC, high-performance computing workforce for computational achievements. So here is the glimpse of our NSM systems. Till now, we have deployed, as I told, 30+ NSM systems all over the country. Soon, our next supercomputer of 20 petaflop will be coming in next few months. So all the NSM systems that we have deployed is of heterogeneous nature, consisting of CPU, GPU, and few fatty nodes into the system. So there is a challenge in application porting since it is a heterogeneous system. And Rudra here, one term I have mentioned. So this is the name of our systems. It's Param Rudra systems. So on heterogeneous system, there is a challenge in porting applications. Since our Rudra system has CPU, GPU, and few fatty nodes, porting is key to use all resource efficiently. Then there is one more challenge, which is legacy code limitations. Most applications are CPU-centric and can't exploit modern architecture. There is another challenge, which is we have to rewrite the code if it is specifically into CPU. Then we have to rewrite the code to port it onto the GPU, which is another challenge. Then optimization, complexity, performance tuning varies across CPU, GPU, and memory types. Then reproducibility is another issue, because when we are porting the code from one system to another, for definitely architecture will change. So we have to keep in mind about the performance that we have previously generated, and then reproducibility is an issue. So here is how we are leveraging Kokkos cutting-edge C++ performance porting framework to make HPC applications run efficiently across the heterogeneous architecture of NSM supercomputers. As HPC systems grows more diverse with a mix of CPU, GPU, and sometimes some other vendor tool chains. So there is a growing need to write code that is both portable and highly performant. So the NSM systems has long support cutting-edge scientific workloads, and with our upcoming 20 petaflop, as I told, machine systems, we anticipate an even broad demand for performance and portability. In this context, Kokkos offer an ideal programming model. It enables us to write code and deploy across architectures. Means write once and run anywhere, like CPU or GPU. So at this point, everyone is aware of what Kokkos is exactly. So I won't be diving deep into that. We'll be having a brief of it simply. So it's a C++ performance portability library for writing platform agnostic codes, which targets write once and run efficiently on any architecture. So Kokkos has all the challenges we have faced in porting the applications from a system from system to different architectures. So Kokkos has helped us addressing this challenge by enabling a single source programming model that can target multiple backends like OpenMP, CUDA, and HIP. This not only saves deployment time, but also ensure scalability and maintainability of scientific codes across NSM platforms. Here you can see that applications are there, and there is a framework Kokkos in between. If we are adding, then we are able to run the applications onto multi-core, many-core, APUs, and CPUs and GPUs. And typically achieving peak performance on each platform requires writing separate code parts tailored to each hardware type, one for CPU, another for GPU. So much of efforts we don't have to put once we have to add the interface of Kokkos, and we are able to run it. So observation and expectations are like we have observed Kokkos is efficiently hides architecture-specific complexities. It is facilitating fast prototyping and production-grade performances. But we have some, like the expectations is that we want expanded support for more programming languages. So on day one, we were having our poster of Anuga, which is a flood prediction modeling system. We have taken like tons of efforts to port it onto, since it is a CPU-centric code, so, and it's very compute-intensive code. So we have to leverage the benefits of GPU for the computational part. So we have ported this code onto the GPU. And since it is developed in Python and C, so we are expecting that in later days we'll get a support of other languages as well. So in practical parts, we have experimented a few mini applications to leverage the benefits of Kokkos onto NSM systems. First, we have tried with mini-MD, which is a mini molecular dynamics, is a parallel molecular dynamics simulation package, which is written in C++ and intended for use on parallel supercomputers and new architectures for testing purposes. So we have deployed this particular application successfully onto the NSM systems, and we have run it on CPU and GPU. Another one we have tried with mini-FE, which is a proxy application for structured implicit finite element code. It is similar to HPCCG, which is one of our benchmark suite, and it provides a much more complete vertical covering of the steps in this class of applications. So both of these mini applications we have deployed onto the NSM systems, and it's working absolutely fine with CPU and GPU. One more experiment we have tried, it is KEDM, which is Kokkos empirical dynamical modeling framework. So the goal of it is to provide an optimized and parallelized implementation of EDM algorithms. In this particular framework, we have experimented elapse, calculate distance, and partial sorting matrix algorithms. We have successfully run it on CPU and GPU, and we have gained, comparatively, we have gained 6x, 10x, and 2.4x speed up on GPUs. So in future we are planning to explore G2C3, which is a global gyrokinetic code using cylindrical coordinates, is a particle in cell. It is developed by C-DAC only, the members of C-DAC, which is developed at the Plasma Theory Group at the Indian Institute of Science to study kinetic instabilities and magnetically confined fusion plasmas. The current status, it is CPU based, so in future we are planning to port it onto GPU. Another one, as I previously told, Anuga, so it's a hydrodynamic modeling tool. It's a free open source 2D hydrodynamic model used for simulating various hydrological hazards like tsunami and other hydrodynamic disasters, disasters that happens. So it's simply a flood, it's a flood prediction model, and this is also CPU centric code. So we are planning to port it onto GPU when we'll be getting support for other languages. Yeah, thank you.
Thank you. Thank you so much. Thank you so much. We have time for one question or so. nobody asks one, I will do. This is not a threat, it's a promise. Have you looked at PyKokkos at all? I saw that one of the future work things you looked at were the last thing, Anuga or something like that,
Anuga.
right? As a Python code.
Yeah, it's like the computer-centric things is implemented in C and Python.
Oh, it is already.
And, to interconnect, we have used Python in between.
Yeah.
So it's kind of a little complex code.
Yeah, so the previous talk, right, was from somebody who actually there's this PyKokkos package, which allows you to write Kokkos-like code in Python directly.
Yeah.
And that might be something worth looking at.
Yeah.
Yeah. Okay, thanks.